So let's go back. Last time I talked about this already. It's good to review one more time, and then I can talk about the other topics. The first paper we study is the cryogenic operation of FinFET from this paper. What we learn, the main point is the structure of FinFET, right? I hope you get familiarize yourself with this. We have substrate, and then we have buried oxide. On top of that, we have the fin, right? This is the silicon. Usually it is the silicon. Let's assume this is the silicon. It can be silicon germanium. So that is the transistor. And this is SOI FinFET because it's on top of the buried oxide. This is silicon on insulator. We have the gate, right? And then we have fin. This is the drain. This is source. The current travel from drain to source controlled by the gate. And particularly, I emphasize that you should know that if we do a cross section, I'm cutting here on the screen, right? Then I will see this fin, right? This is the silicon. Current is traveling perpendicular into the screen. Is that okay? If you have a question, you should ask now, right? That's why you come to the class all the way so late. Otherwise, why don't you just stay at home to watch the video, right? Attendance is not affecting your grade, right? So you go inside, right? And a typical structure is like this. It has an interfacial oxide layer, SiOx. X is unknown. It means that it's not stoichiometric. It means the X can be 1, 1.5, 1.2. It's not stable in some sense, but this is oxide you may form by using just chemical, put it in HF. Is it HF? Any oxidizing agent or hydrogen peroxide, right? Then you form a very thin layer of silicon oxide. On top of it, then you grow this hafnium dioxide. You deposit hafnium dioxide, which has a very high electropermittivity, can be as large as 30 or even larger. The reason is because we want to increase the capacitance. And then on top of it, we have the metal. We have the metal to adjust the work function. In the class earlier, we also mentioned that for FinFET, we want something that has a work function close to the mid-gap of silicon. Right? The valence band of the silicon, maybe you forgot or you didn't know, but anyway, I can say a little bit more. If this is the valence band, this is the conduction band, and then you go all the way to the vacuum, right? To the vacuum. And what is the energy for electron to go to vacuum? This is about 5.1 EV. And from conduction to vacuum is about 4.05 EV, approximately. I forgot the exact number, right? And what is the meaning of mid-gap? It means that I want to have a, right, work function about 4.5 EV. That is what you mean by mid-gap if you read papers. A work function that has an energy about the mid-gap of silicon. It just means that it's about 4.5 EV, 4.7, 4.4, instead of 4.0 and 5.1. Okay? So I hope you understand this, yeah?
I have a question. I'm trying to relate. Say that the valence band is fires the product from the box, really steep or really tall walls, really high potential energy, and induction band is still the part on the box, doesn't much shorter, I guess. Why is the potential energy?
I won't say that thing in a particle in a box in this way because this is just the results, right? If this is not necessary, not need to understand, but you can think it in this way. If you have an atom, you have the 1s orbital, you have the 2s, 2p, 3s. Each of them have different level, right? For example, hydrogen from 1s to here is 13.6 eV to vacuum, right? 13.6 eV. That is the energy you need to put to ionize an atom. So you have this discretized level. Now, of course, now then you say why you have discretized level? This is just like particle in the box. although it's spherical, but because due to confinement or periodic requirement, that's why you have discretized energy level in the atom. When you bring all the atoms together, instead of just one atom, you have 1e23 atoms. Well, a lot, right? Then this energy level, for example, 1s, 2s, 2p, you can imagine that when they are far, far away, then you have a lot of this this energy. But when you bring them together, they will start hybridize, and then because it's no longer an isolated atom, so you will start having this splitting to many different levels within a band, right? Something like that. Same for 2s, right? So they may merge when they are so close. This is the distance. When they are getting very close, right, they may become this. And then maybe, this is just a fake example, then maybe the bottom one all got merged, right? And then, of course, you have those so-called anti-bonding also, right? They won't fill up because now you merge them, then they won't fill up all the way to the top. And the so-called conduction band and valence band is just that there's a band gap in between, right? And for silicon, it turned out that they all fill up those right below the band gap. And then conduction band is completely empty.
Actually, I'm thinking this is actually if we put put the FET in magnetic field and split that doesn't work. Maybe we actually control it that way. That's sort of another way to control the band gap.
Controlling the band gap, you say put in some ferromagnetic. Yeah, so then then you need to. You need to have the Hamiltonian, right? If your material can have a strong interaction with the magnetic field, then you can do that. But for silicon, this is what we get if you don't apply anything. But there's something called spintronic. They may have some effect on that, but it is not going to be very large. We're going to about small level. Yeah, you can do that. But obviously, by doing stress and strain, that has a larger effect. Okay, so yeah. So in reality, they all merge. It doesn't matter what model, the physics is there. Tight binding model is a method to simplify the calculation, right? Okay. Okay, so we are too far. So just for your information, right? So it's good to discuss. But do you understand all this FinFET structure? Then last time we talked about the change of threshold voltage. I think we understand very well when you reduce the temperature, threshold voltage will increase because of two things. If you remember, one, the band gap increase at low temperature, right? Two, the Fermi level move closer to the band edge, right? And this is the same for the fully depleted silicon case, right? Again, it increases when the temperature reduces, right? There's so many things in this class, but this type of concept you need to instill into your brain, right? You have this concept when people ask you, when the temperature goes down, what happened? Subthreshold slope, of course, will reduce, okay? Here particularly, I want to say something. This is the transistor for 150 nanometer for the gate length. And this is for the gate length equal to 60 nanometer. Can you tell me why the subthreshold slope is smaller or swing, right? So they call it slope, right? But we say that some people are very picky, the reviewer, they say we should use subthreshold swing. But actually, I do not agree with them, although I always change it because they're reviewer. Because I think this is just a tradition, right? We can call it swing, right? I don't know why they always want the reviewer, right? They always say that, hey, this is not the slope. What we are showing is not the slope, it's 1 over the slope because this is the current, this is the voltage. But can they just rotate the graph by 90 degrees? I don't know why the reviewer want to insist this is not a slope. And rotate by 90 degree, it is a slope, right? But anyway, but I always listen to them, change to swing, right? But in the old literature, you very often see the slope. Okay, now, then why it is improved when we increase the channel length? Say, do you remember?
The N factor that's function of capacitance.
The N factor, yeah, he is talking about the subthreshold swing equals to KT over Q, not 10 times N, right? Where N is 1 plus C depletion divided by C ox. But that is not very directly we can relate. What do you call this effect? Short channel effect. That's just something I try to fish. But you can say because of short channel effect, the N factor maybe got worse because it is no longer correct. Yeah, but I'm trying to fish for this word, SCE, due to short channel effect. So you see the same thing in the FinFET, right? FinFET is no different from traditional device in this regard. Okay, now how about transconductance, right? If you just look at the low fin width, which is small, what is the meaning of fin width? Now we are looking at this. This is the fin, right? Maybe this is 100 nanometer, and then this is another fin. This is 1,000 nanometer, which is very wide, right? So if this is 1, this is 1. If this is 2, this is 2. Okay, and then you have the gate surrounding it. This is the gate. Okay, now, so if I have a small fin or large, small fin width or large fin width, regardless of which one, when your temperature increase, the transconductance increase, which makes sense, right? Why? Do you remember? When temperature reduce, transconductance increase. Less photon scattering, so better mobility, right? Okay, good. Particularly, can we look at this? When the fin width is wide, the increase is more. Say again?
It should increase the current.
It should increase. The increase in the GM is more. This is normalized, right? So this is because we have different orientation, and also for the narrow fin width is mostly dominated by the surface roughness scattering. So the effects of photon will be smaller in that sense. Okay, so you need to think about different things, right? But no need to go so deep, right? The point is at lower temperature, the transconductance increase. Right, so later when you design your L10A, you should know that you get better transconductance at lower temperature. That's why you want to operate at cryogenic, right? Now here, also talk about transconductance as a function of temperature. So let me just quickly show that, yeah, it increases. When you reduce the temperature, the transconductance increase, okay? But the reason I repeat what we did last time is that I want to talk about GM over IDS, this concept. So what is GM over IDS? Why people care about this? It's mostly the analog circuit community. And it is also for those trying to have low, not really actually, but very often those want to operate the transistor as subthreshold regime to have a very low power consumption, right? So let's take a look. Did I miss something? Yeah, just remind yourself what is, maybe actually I use this slide to remind you what is GM first, okay? So what is GM? GM equals to partial ID, partial VG, right? And if you remember, we will do this from the ID VG curve, right? And that is why I'm saying I keep repeating something we have learned. I want to have this type of immersion environment, right? So that's why you need to pay attention in FE classes, not just wait for another month or two and then come back to say, oh, these are difficult. If you pay attention, keep asking, eventually you know what we are discussing. So what is the curve? Do you remember how does the curve look like for IDVG when it is linear? Go up, right? Someone say you will go up. Linear, yeah. Almost zero here, right? And then VTH go up. Now, but then I also show you this before. Do you remember why this does not go up as fast when you reach this region? It actually will not, due to velocity saturation, because your VG is only increasing the gate voltage, right? You do not increase the electric field in the transport direction, right? Well, for velocity, it's like, so it's good to review. That's why the discussion is useful. If you look at the transistor, you have N plus here, your current go from here to here. You have velocity saturation only if your electric field is in the same direction as the transport. It's moving from left to right. When you increase VG, you only increase the electric field vertically to get more electron and push it against, right? So what is the reason? I already give you a hint, push it against the wall. When you increase VG, what happens?
It's hitting the surface.
Exactly, right? So you're pushing me against the wall, I get more scattering, right? Because when I run from this side of the classroom to the back, and some of you keep pushing me against the wall, my mobility will reduce. That is one thing, right? So what type of scattering is this? Surface roughness scattering increase. Another is because the current is large, so the contact resistance has effect. When you're measuring the transistor, do not forget that this part has a resistor. And also when you go to metal, you also have a huge resistor from metal to silicon, right? So these are the RC. They are constant, but now if you have a big current, it will give you a IR drop. And then as a result, you actually have less effective voltage across this transistor. Make sense? So if you plot the GM, how would it look like? You plot the GM. As we said, we are just doing the IDVG, right? If this is GM, this is VG. You are doing the differentiation. This is very small. And then it will increase. And eventually you will reach a peak and then decrease again. This deduction is because of this change of the slope. And that is this, what we call GM. And that is what we have. This point is GM equals to GM maximum. This is what many analog circuit designer or RF designer care about. What is the maximum GM that your transistor can give? Yeah. It's not negative. I did not give you. Did I give you negative? This is 0. No. This is 0, right? Okay, good. But good point. You will see negative. I thought I showed you negative GM before already for SOI or a bulk transistor. Maybe I went too fast. Yes, I had a slide about negative GM. That case sometimes happen. We also saw this in experiment. That is just because the surface roughness becomes so dominating. So in principle, you can go small to have a smaller current. We do see this in experiment. Right? Okay. Okay, so if it's confusing, but the purpose you come to this class is to learn the basic, right? I hope that you make sure that you understand what is GM. If I give you this curve, you can sketch what is GM. And another concept is there's something called maximum GM. And if you forgot why there's a maximum GM, at least you remember there's something called maximum GM, right? You don't know why, fine, but you need to know this. Otherwise, how can you go through the interview? Okay? Okay, so I talked about this GM, right? So let's look at the derivation. I think I don't have space. I should start from here. And this is not from line already. Actually, we did not really cover last time. So first of all, what is ID? So we have two regimes, okay? One is the subthreshold regime. The subthreshold regime. So what is ID? Do you remember? Drain current, yes, sorry. I mean, what is the equation? But in subthreshold regime. Yeah, that's good enough. Exponential. If you forgot, just because I did not emphasize, right? We did a little bit before, but it's great that you remember that it's exponential. Now you remember exponential, exponential VG related to the gate voltage divided by KT over Q. And there's a ideality factor, but let's not worry about that, right? Then what is GM? Q. Oh. Yeah. So if you do GM, it becomes I0. I mean, what is the equation for GM again? Thank you. Yeah, I know I'm repeating, but you need to keep repeating to remember and understand, right? So this is ID. Then you do the differentiation, right? Exponent something. Then the exponential term doesn't change. You take the prefactor out, right? Because it's partial VG. So whatever there, not including partial VG, will be taken out. And then you see this I0 exponential QVG and KT is just ID. This one I need to write it clearly. It is not I0, it is ID divided by NKT, right? Because this term and this term are just ID. Is this okay? Q is positive. This whole term is positive because when you increase VG, the current go up exponentially. You are right. That was reverse bias diode. You get negative if you reverse bias. Yeah. So then what is GM divided by IDS, which is ID, right? What is that? GM divided by ID, what is that? Based on this equation? Q over NKT. This is very interesting. So no matter what transistor you have, this is a bipolar transistor. The ratio between GM and ID depends on Q, well, on T only. Okay? Doesn't depend on how you design your transistor. So that's why people say, I get a very large ID, but knowing is useful, of course, but from energy perspective, you need a lot of energy in order to get large GM, right? So you need to, so that's a trade-off, right? So the lower T, so you look at the temperature, when you have a lower T, in this subthreshold regime, right? This is subthreshold because it has low current for a different current, right? This is subthreshold. Maybe I would say it's difficult to distinguish, but I would say this is subthreshold. And this is on state, right? Of course, when you increase T, your GM over ID increase a lot. Okay, that is the first thing. Any questions? And that's why you get this equation. Q over NWI dot KT, which is not 10 divided by S. Yeah. Charge, yes. No, Q is the elementary charge. Q equal to 1.6 times 10 to the power negative 90 Coulomb. Yeah. At cooler temperature, which is what we have been expecting, right? Okay, then how about the on state? Now that is the equation you told me earlier, right? ID is proportional to, well, if I do it, that's going to take a long time, but okay, let's do it. W on L, mu C ox Vg minus Vt square divided by 2, right? So partial ID, partial Vg, right? This is just an exercise, equals to W on L mu C ox Vg minus Vt. Okay, so this we learned in E124, but if you forgot, that's fine. Just do a differentiation. This 2 and this 2 cancel out when you do differentiation. You got this, right? So we will further show that this is equals to, you just plug in, you will find that this is true. 2ID W on L mu C ox. Okay? And then you just go through them, and this is GM, of course. Then if you want to find GM divided by ID, eventually you will find that it actually depends on the ID itself. If I have a larger ID, I actually have a smaller GM over ID, not that efficient. So in this regime, I actually want to go to smaller ID, and then I have larger GM over ID. So efficiency is better. When you are in this regime, you also find that it does not depend on temperature. So in the on state, right, if you have a large current, reducing the temperature will not help the GM over ID. Okay, so you want to more operating your circuit in near subthreshold regime instead of fully on regime. Of course, this approximation, we did not take into account all those degradation or etc. But, okay, so many things. What do we want to learn? One, we appreciate that in some circuit community, they care about GM over IDS because IDS represents the energy efficiency, GM represents the performance of your circuit. So we want to have the ratio, use this to compare. Second, we learn how to find the GM over ID for subthreshold region and on-state region. This is a simple math, right? It's okay you forgot the equation, but it will be good to remember subthreshold is exponential. This is quadratic. Or it is linear when there's a velocity saturation. I don't know if you remember what I taught you earlier. At that time, GM is almost constant. Okay? Then the last thing is understand the temperature effect, right? If it's subthreshold, reducing the temperature, it has a big effect. It's easy to memorize, right? Because subthreshold depends strongly on temperature, exponential. But when it is on state, it is not as much. So when you design your circuit, you can take this into account to help yourself, okay? Yeah. Just from the equation. Of course, the mobility also changes. So this is important. Small depth dependence, but look at this. No, it is right. So because when you, it has some little dependence, mobility, but then the current also depend on that. So when you expand them, you get some weak dependence, but not that strong, right? Yeah. So think about this, right? When you want to have a harvest the effect of cryogenic circuit, right? But of course, I need to admit, these are all toy models with a lot of approximation. If you really want to do something, you should maybe use BSIM to do a simulation, right? Yeah. Yeah, but then you need to specify what is Vg minus T, Vt, which determine IDS, which is, yeah. So you will have that problem. But it definitely say that if you have larger Vg minus Vt, your the whole thing is like not temperature independent.
It seems like in that case,
Yes, you're right. If you plug in this, you're right. Yeah, if you plug in, then it doesn't depend on the first order. Yeah, but of course your VTH is changing, and also now really depends on whether you have saturation, velocity saturation or not. Do you still remember? If you forgot, right? Remember we talked about, I will erase it because it is messy, but let me put in the lower left corner. When you have velocity saturation, the current is proportional to the charge times the saturation velocity times Vg minus Vt, not square. Do you remember this equation? Anyone remember? I mean, remember that I taught about this equation. If you did not study, you won't remember, but I taught about this. Then partial ID, partial Vg is just a constant, right? Gm is just Q times Vset. And then Gm is just, and then Gm divided by IDS will be 1 over Vg minus Vt, which is also not dependent on temperature. Yeah, so yeah, I did not study this, but this is something we can try in the midterm. Yeah, I give you the equation, you tell me, but I realize maybe too much material here, so yeah. Okay, any questions? Yeah. Hold on, when did I say that IDS goes up when GM reduce? This one? This, hold on, so this one, where does it say when IDS reduce, no, it's GM divided by IDS. Yeah. Okay, so we're talking about GM divided by IDS. Okay. Okay, good. So another thing is R out. So this one, let me spend a little bit time. What's R out again? Do you remember? We talked about this. Yeah. So here we have the VD, ID. What type of curve it is? ID, VD curve, right? Not ID, VG. Right? We have two types of curve, which I emphasized at the beginning, right? And this slope, the slope of this one is 1 over R0, which is equals to, right? The slope, of course, is partial ID, partial VD, right? But the definition R0 is partial VD, partial ID, right? Just inverse of it, correct? So if this is steeper, then it means that the R out is smaller. When this is flat, right? When this is flat, what is the slope of this graph when this is flat? 0. But 1 over 0 is what? Infinity, right? The slope of this graph is partial ID, partial VD, which is 1 over R0. R0 is partial VD, partial ID. That's why, just like what I said, you rotate 90 degrees, then you will see what is the meaning of that one, right? Okay, so it turned out that when you reduce the temperature from here is 380 Kelvin all the way to 150 Kelvin, this slope is actually larger. 1 over R0 is larger, which means that R0 is smaller. Here shows and then we need to introduce another concept. R0 is the output resistance, right? It's 1 over the output conductance, GD. Okay, so this is GD. So you have a transistor. This is D, this is S, right? This is gate. And we are talking about when you change VDS by 1 unit, how much current IDS is changing? If you do VDS divided by IDS, of course, that is the output impedance. If you do the reverse, it's the output conductance, right? Just resistance and conductance, take the reciprocal. Let me pause a little bit. Is this concept clear? But this is a very important concept, right? If you forget everything. Any question about this output conductance and output resistance? No, we don't, right? When we do the gate, it's the GM, right? How the gate changing the drain current. And the gate is supposed to be insulating, so we don't care about IG, VG, partial IG. Yeah. So for a transistor, we only care about how the gate voltage change the output current, which is the trans conductance, and how the output voltage change the output current, which is the output conductance. What put? Of course, you need to turn it on here. I assume it is a constant bias, and then you change the output voltage to see how the current changes. Just like each of these curves is biased as a certain gate voltage in IDVD. You need to specify the gate voltage you are talking about, definitely. Yeah. If you remember, it's good time to review. This is VD, this is ID. Remember, I have curve like this. This might be VG minus VT equal to 1, equal to 2, equal to 3, right? So at different VG minus VT, I have different slope, and that is what you are asking. Yeah. Any questions from the quiet students?
Oh, sorry. Yeah, you said we're in the figure there.
Yeah, but I don't expect you to read it. Just ask me, right? You don't have time to read every word. Yeah. The transistor. Yeah. So this is IDVT curve on the lower left, right? This is for a given VG. Then you have one curve when you sweep VD, right? Because larger VG, you have more inversion charge. Then you have larger current. And this corresponds to this graph. If I say this VG is biased at VT plus 1 volt, then when I change VDS, the IDS will change according to this curve. When it is 2 volt, then it changes according to this curve. So when I claim it has a certain output conductance, which is 1 over GM, which is measured by partial VD, partial ID, right? Then I need to specify which gate voltage I'm talking about. And that's why when you design your circuit, people will say how you bias your transistor, right? You bias at which voltage, gate voltage. And then you talk about the output conductance. And that's okay because for RF, most RF and analog, we operate in small signal, right? So you have a DC bias. I bias at 1 volt, 2 volt, 3 volt. Then you operate at 3 volt, right? All the thing fluctuate around that quiescent point. So here it tells us that the GD increases when I reduce the temperature, then GD, right? Then what is the R out? Here you say GD increase, then it means what? R out, what happened to R out? GD increase, R0 goes down, right? Because R0 equals to 1 over GD. Which is bad, because we have not discussed this before. The intrinsic gain of a transistor is GM R out, okay? We did not discuss this, take it for granted. We will talk about a little bit about common source later. At that time, you understand why. But GM R out, what happened to GM when we reduce the temperature? Goes up. Now we say what happened to R out? goes down. So there they got canceled. Now, so it depends on the technology. For example, in our experiment, my experiment, when you go to 77 Kelvin, 100 Kelvin, this whole thing goes up. But when you go to 4 Kelvin, the whole thing is only within 10% difference, maybe increased by 10%. Right? We have some FinFET data even almost the same. Right? So this is a bad news. So you hope that to cool it down, you have better performance, but turn out it is similar to room temperature. But only from this perspective. There are still other perspectives, including reliability, noise, which can get improved at low temperature. Okay. And this is what I talk about the intrinsic gain. AV equals to GM times R out, right? So you see that it goes up when you go to lower temperature, but then actually it goes down. For this particular FinFET, actually it kind of, yeah. But again, huh? Yeah, here, right? They turn out to be 300 is the best, right? But here I emphasize it. This is an old paper, 2008, and it's from a university laboratory, right? So the trend, right, the shape should be correct, but who knows, right? Because their material are not as good as the industry one nowadays, right? So you cannot take this, assume this is for everything, but that is what you can get. Okay, so this is very important, right? Their paper are good, but remember, do not just use their stuff directly. Okay, so that is the first paper. Second paper is newer. I forgot the year. It's newer, but here just again to show you different structure. This is another FinFET. Now, is this a SOI or a bulk FinFET based on the drawing? Bulk, right? Because the fin is connected to the substrate, right? So last time we talked about how to manufacture SOI and bulk FinFET. If you forgot, go back to take a look. But definitely, they etch the silicon substrate to form the fin, and then deposit oxide and recess so that you have this bulk FinFET. And then the rest are the same, right? This is the drain, this is the source, and then you have high K dielectric. And again, they have hafnium dioxide, all this very complicated metal. This gives you a sense of the dimension. This is the fin, right? This is the fin height. This is a TEM picture, transmission electron microscopy. Nowadays, transmission electron microscopy can resolve up to atomic level. You can see individual atom. Transmission electron microscopy, right? So they thin down the sample to very thin and then shoot the electron beam to it. Now the electrons are just like their wave, because they're very short wavelength, so you can resolve very tiny feature, right? This one is not a good one because for 35 nanometer, of course it might be good at the time, or not an expensive one, right? People can resolve very, even see the crystal structure, but this is good enough. Here is the curve, nothing else, not much to say, only want to say what is the meaning of the overdrive. That is exactly what I talked about earlier. Yes. VGS minus VT, right? So this is what type of curve? IDVD or IDVG? IDVD, right? So each of these have a given VG. VG equal to this, VG minus VT equal to this, right? So at 300 Kelvin, you have this, and then for 10 Kelvin, you have this. You do see increase in the current. Now, if they did not plot this, they only plot VG, you probably will see that they are similar. That is because now they take this increase in threshold voltage into account. Yeah.
I think that's why overdrive is helpful, because it's agnostic to how much you teach. So you're looking at how much above the device.
That's right. But then in real application, you need to have the ability to reduce the VT to that level in order to gain that current. I understand why. So that's a good discussion. Let's think about what he's saying. So this is the curve in log scale. And maybe this was the 300 Kelvin curve. And then we try to measure the 10 Kelvin. Maybe you get something like this. Very similar, but only a little bit increase. And he's saying that, okay, we are only looking at the overdrive, so maybe for this point to here is equivalent to this point to here, because this one has larger VTH, right? But in reality, yes, of course, you're right. But remember, we can only operate it to VDD. Otherwise, the reliability issue, power consumption issue can be a problem. So if you want to enjoy this overdrive, then you need to be able to reduce this. But at the same time, you also make the reliability worse. Right, so you need to find a way, right? Change the work function or whatever to reduce the VTH. But you are right, this is the fair way to compare how much current increase you can have. But on the other hand, it does not mean that we can modify the process to get this improvement. But definitely we can reduce the voltage. I mean, we reduce the threshold voltage and reduce the VDD at the same time. Maybe that same current, but lower power consumption. No, yeah, this one can use body bias, but its SOI will be difficult, yeah. Yeah, but that's a good discussion, right? So he's saying that to do fair comparison, maybe you really need to use overdrive. How much more do you bias over the substrate, the threshold voltage, okay? I feel I'm very slow, so then this is just the same, GM will increase, right? Maybe I just, let me go a little bit, yeah. We don't say we are over, so this is something, how to say, confusing. When I say overdriving, it doesn't mean that you are working over the specification. It's not like in the old time, your CPU overclock, right? You make it 100 gigahertz become 100 megahertz become 400 megahertz. We don't mean that, or higher voltage. Here it's just a definition of voltage overdrive is VG minus VT. We find the difference between VG and VT because only after VT when you get it, it would turn on, right? And so only that part really constitute to the property of your transistor. You know, just like what nowadays we talk about, I don't compare your GPA directly. I will subtract all the, for example, your education background, right? Because you are much poor, you don't have all this extracurricular activity. I try to find the difference between, have the same base point. And then over this overdrive, then I compare whether you are better scholar or not the absolute performance. Make sense? No, you need to VG need to be larger than VTH in order to turn it on, right? Yeah. So if one has the threshold voltage 0.4 volt, one has 0.68 volt. You cannot apply 0.5 to both of them and say that this transistor is good, it has current, but this is very bad, it has zero current. But just because you put it below the threshold voltage, right? So I will put this 0.5, for here it will be 0.78. Then I compare the current, then I say, oh, this one is better or worse. Okay. Same for the subthreshold and GM, they're similar, okay? This is another SOI FinFET. The thing we find, this is SOI, right? Because a box here. Interesting thing is here, you have a fake top oxide, top insulator. So because of that, you only have two channels on the side wall. Right? This is one of the common FinFET that you have. Right? Because this is so thick, it cannot act as a gate, although you have a gate on top. So you only have the current flowing along this line and this line. Yeah, you can say that, or it's so thick, so you have very weak field. Yeah, right? Just as if you were not there. Imagine it's infinity, right? You cannot have control. So you don't get inversion here. So maybe this is the main point I want to say, right? Okay, so let us quickly, even not looking at the figure, maybe you tell me, when the temperature increased based on this figure, let's look at this figure. What happened to the VTH? This is 300, this is 8 Kelvin. What happened to the VTH, threshold voltage, when the temperature reduced? It becomes? Goes up, right? Are you okay? Everyone can read this graph? It becomes here, right? I mean, you will get this in midterm. If you don't know, can you ask me now if you don't understand? Yeah, it get larger and larger. Okay, what happened to mobility? Maybe it's easier to see from here, right? Mobility determine what? By the way, if you get confused about this graph, let me remind you, this is always read the S's, ID, VG. And this is log scale, but it plots PMOS and NMOS together. This is ID, VD. It plots PMOS and NMOS together. If you are not comfortable with this, just look at the NMOS part. This is exactly what we usually say, right? Different VGS. Right here is VG equal to 0, and then 0.1, 0.2, keep going up, right? What happened to the mobility based on this graph where I have a lower temperature? Yeah, you get higher, yeah. Because I did not plot mobility. How do you know that it goes up? Huh? No, I mean, I did not plot the mobility based on this graph. How do you know it goes up? Here we look at the current. Yeah, the current goes up, right? And you can start arguing, it goes up, is it because the threshold voltage is lower? Because now for each of this curve is for fixed VG, right? Can it be threshold voltage becomes lower, that's why the current goes up? No, we just say that the threshold voltage goes up, right? Instead of going down, right? Not the threshold voltage going down. So threshold voltage goes up and then the current still go up, then is it the capacitance goes up? Probably not, right? So the only thing is the mobility goes up. Right? Any kink? Do you see any kink? Do you still remember what is kink? You know that. So instead of no imperization, you will say that there's no kink effect. Maybe there's still imperization. However, it is fully depleted because now the FinFET is very thin. So it just like FDSOI, although the body is not connected, but it is fully depleted. So even you have imperization, you don't have accumulation of hole to cause the kink effect. Make sense? Now again, I hope you understand the style I'm teaching, right? This is the third time I mentioned kink. Maybe you still don't understand, but really pay attention to every slide, right? We talk about this in the bulk, in SOI, and now FinFET again. And they all share the same physics. The bulk is a little bit different due to the freeze-out effect. Okay? They also try to use this FinFET to create a differential pair. This is single-ended differential pair amplifier, very bad gain. Oh, no. I mean, the gain was low, I remember. DC, no, not 59 dB actually, not low. Right, and then they make this in a unity gain buffer, which probably some of you don't know what it is if you forgot the E124, E122, but doesn't matter. The point is just to show you that they perform well. You do not expect this one to have a higher gain because it should act as a unity gain buffer. By the way, 0 dB means gain equal to 1, okay? dB, you convert something into dB, is by taking 20 log the gain. Okay, but we will discuss more later when we talk about L10A. This is a good video also, right? I found it from internet. Take a look, it's pretty new. I forgot when it is, but it's like 2019 or something, right? From, I think it's from ETH or EPFL, I forgot which one. Okay, so take a look for this presentation. they talk about their measurement. Okay, any questions? Okay, if no, looks like I don't have time to do the layout demo.